All right, we're here off to still solutions, I think. And last time we were talking about really concentrations, and we talked about some different types of solutions, which is percent m/m, which is mass to mass, which again is the mass of the solute divided by the mass of the solution times 100%. We also saw percent volume to volume, which is our volume of solute over volume of solution times 100%. And our percent mass to volume here, which is our mass of solute over volume of solution times 100%. Remember, with these percent concentrations, you can usually kind of turn them into a conversion factor, as we talked about, really assuming 100 of whatever it may be. So if we had a 1.75% by mass here, calcium chloride solution, that would mean we have 1.75 grams of calcium chloride over 100 grams of solution. And again, you could flip it around if you needed it like a conversion factor the other way. Put the gram solution up on top to 1.75 grams of calcium chloride in this example on the bottom. You could also do that for the other. So mass to mass is grams over grams. Volume to volume is typically milliliters over milliliters. So you would have something like 1.75 milliliters of calcium chloride over 100 milliliters of solution. And mass to volume is grams over milliliters usually. So that last one would be something like 1.75 grams of calcium chloride over 100 milliliters of solution. Remember that out of all three of these, this is the one you really do have to watch out for when you're doing problems, as they will give you that sort of solution kind of separated out in the form of its solute and its solvent. So they'll oftentimes give you those numbers separate from each other. You want to make sure that you do add it together. Again, as we talked about, a very common mistake is people will just divide by the solvent and not really the solution. So you want to make sure you have both of those when you do it. We then talked really about probably the most common unit of concentration, which is molarity, which is our moles of solute over liters of solution. And we do think of molarity really as like a formula. Molarity is moles per liter. And we can solve for any of these three things. So liters would be moles divided by molarity. And another very common one used a lot is moles is liters times molarity. Really important, as we talked about last time, and we'll continue to talk about, is if you are using molarity and you are using volume, it needs to be in liters. Otherwise, you will probably be calculating the incorrect thing that you're looking for. And remember, thank you. To convert between milliliters to liters, there's 1,000 milliliters in a liter. So that's, again, a conversion that's used a lot. Also with molarity used a lot is like what we did last time is molar mass, to take grams to moles. So molar mass from the periodic table to convert our grams into moles. We also mentioned that, in a lot of cases when you are doing problems that involves molarity, it is oftentimes a good idea to get rid of the big M and take more of a dimensional analysis approach when you're doing this, because a lot of people, when they see the big M, they just for some reason think moles instead of molarity, and they forget all about the volume part. So a lot of times people will forget all about the liters part, not really sure where it's at, if it's even there. So a good way to do that is to take more of a dimensional analysis approach when you're doing these problems. And if you have something like 1.75 molar calcium chloride, basically that means that you have 1.75 moles of calcium chloride per liter of solution. The number always stays with the moles part, and it's always per 1 liter. And again, you could flip it on its head there and use it as a conversion factor. And again, you could put the liters up on top, the moles on the bottom. The benefit of this is you can hopefully clearly see both of the units that are involved, and not get into a common, again, error that people make, and they just have no idea about the volume. So why that's important, again, is some cases you may not know if you should multiply by the volume, divide by the volume, because you can't see that unit. So by getting rid of the big M, taking a more conversion factor dimensional analysis approach, you're able to really see those things a lot easier, both of those units. Any questions on any of that there? So we skipped ahead on an example. So let's go back to a couple of those examples we skipped. So why don't we try this one first? We also talked a little bit about ions and how concentration works. So why don't you take a couple moments, and for each of these are two separate sort of problems. For each of these individual solutions, we want to know what are the concentrations of the actual ions that are present in each solution. Remember that when you have a solution that's an ionic compound, it's ionic, which means there's a strong electrolyte. It's going to break apart into ions. So really what's floating around that solution are the ions, not the whole units together. So they've broken apart. We'll take a couple moments here and calculate the concentration of each of the ions in each of those solutions, what their concentrations would be. Let's take a look. So as we talked about last time, in a solution that's an ionic compound, because that's a strong electrolyte, we will really just have ions that are floating around in the solution. So sometimes you're not interested maybe in the whole thing together, or you may just be interested maybe in one of the ions, the positive guy or the negative guy. So really the first thing you got to determine is how this guy is going to break apart. So if we took our first guy here, our sodium sulfate in solution, it will 100% break apart into two sodium ions and a sulfate ion, basically when it dissociates and breaks apart. So the way that concentration works, as we talked about last time, is if the concentration of this whole thing is 1.2 molar, you could take it like stoichiometry, that this is a 1-to-2 relationship in terms of the sodium ions. And basically you can multiply the concentration by 2 because of that. And 2 times 1.20 molar would say the concentration of the sodium ions in that solution is 2.4 molar. You could also do it for the sulfate, which is a 1-to-1 relationship between those two, which means you could take 1 times 1.20 molar, and basically it will stay the same, which is 1.20 molar would be the concentration of the sulfate in that case. Clearly, molarity is not additive. It doesn't add up, obviously, to 1.2 when you add those together, but it's more proportion-wise. So basically, for every one of those guys that go for a swim, you get twice as much sodium as you do sulfate. So the concentration of sodium is twice as concentrated as it is for sulfate. Question on that. Just also a reminder that what we just did there is sort of the short version of that calculation. The long version of that calculation is we would do like a stoichiometry relationship, taking the molarity of the entire thing, which would be 1.2 moles of sodium sulfate per liter. We would then do our mole to mole relationship, which in case of sodium, again, is a 1 mole of the whole thing. Gives us 2 moles of the sodium ions. The moles of the whole thing cancel, leaves us with 2.40 moles of sodium ions per liter. That is essentially why we are multiplying by 2, is essentially what we're doing there. And again, that's just a quicker way of doing it. You obviously could do the same thing for the sulfate. You would have 1.20 moles of the entire thing per liter. It is a 1-to-1 relationship between the sulfate and the whole thing. Again, the moles of the whole thing cancel, leaves you with 1.2 moles of sulfate per liter, which is what we get here, right? And this is also why we multiply by 1 in that case, because it's basically a 1-to-1 relationship. Any questions on either of those there? So looking at our other one, which is, if I remember, what was it? 0.75 potassium chromate, I think. So we have in this case potassium chromate, which once again, when it breaks apart, will give us 2 potassium ions and a chromate. the -2 charge. And this was 0.75 molar. So once again, kind of taking the quicker calculation, a 1 to 2 relationship means we should take 2 times 0.75 molar. And for our potassium ions in that solution, the concentration would be 1.5 molar. And we could do the same thing, obviously, for our chromate, which would be a 1 to 1 relationship here. And we'll take 1 times the 0.75, which means it will stay the same, 0.75 molar. So once again, this is a way that we could relate sort of the concentration of the whole ionic compound to the concentrations of each individual ion that may be in that solution. And again, some cases you may just be interested in just the ion, a particular ion that's floating around in that solution. So pretty simple. If it's a 1-to-1 relationship, it's the same concentration, 1 to 2 multiplied by 2, 1 to 3 multiplied by 3, basically just multiplied by the coefficient of how many ions you get when that thing breaks apart. Any question on that one there? All right, so let's try another one here. We are looking for how many moles of just sodium ions are present in 42 milliliters of a 0.35 molar solution of sodium chloride. All right, so take a shot at it, see what you get. Again, we're looking for just the sodium ions in this case. Look, so once again, obviously we're dealing with molarity, which is our moles per liter. We are given the molarity of our sodium chloride, which is 0.35 molar. We do have the volume given to us, which is 42 milliliters. And we are looking for the moles of the sodium ions. So again, if you're not sure, we obviously have molarity given to us. We do have the volume not given to us in liters, but in milliliters, but we could get there. So solving for moles would make sense in this case. So there are a couple of ways you could kind of approach this, but whichever way, again, we need liters times molarity here. I'm going to convert this into sodium ions up front. So that means that my sodium chloride will break apart into a sodium ion and a chloride ion. And since the concentration of this guy is 0.35 molar, it is a 1-to-1 relationship, which means I would take 1 times 0.35 molar. And that would give me 0.35 molar for my sodium. Reminder as well that although we do not need it in this question, the molarity of the chloride ions would also be 0.35 molar in this case, as it is a 1-to-1 relationship as well. So since I have that, I also want to convert my volume into liters. So that is, again, a very common conversion. And once again, that common conversion is 1,000 milliliters is a liter. Gives us 0.0420 liters. Now that I have both the molarity and the volume, I'm good to do my calculation. Again, I'm going to get rid of the big M here. And basically what this means is there is 0.350 moles of sodium ion per liter. Or I could use it the other way if I needed to, a liter on top, 0.350 moles of sodium ions. So in this case, we'll take our volume converted to liters, 0.0420 liters. We will use our molarity like this, where our moles will end up on top, which is what we're looking for. Liters will cancel, and that will get us 0.35 times 0.042. 0.0147 moles of sodium ions in this particular case. We could have also just did it with the sodium chloride and then did the mole-to-mole relationship at the end and converted those moles into sodium ions. So you could have done it at the beginning or the end of this calculation. They both would come out the same in this case. Question on that there. In this particular problem, if we did chloride, it would also come out to the same answer, obviously, in this case, in terms of how many moles of chloride there would be. Any questions on molarity here? A reminder as well, as I think we talked about last time, that you can multiply milliliters times molarity, but a reminder that what you get is not moles. You get millimoles, which would put you off by a factor of 1,000 in this case. It's okay if you divide by milliliters because the millis will cancel and leave you with molarity. So always good. And you should always do it if you are using molarity by itself with volume. Always convert it to liters. You'll be in the right unit that you probably need. Again, if you multiply by milliliters, you'll be off probably by a factor of 1,000, not realizing it maybe. So always when in doubt, make sure that volume gets there to liters when dealing with molarity. Any questions on that? Okay, another important topic is, as we talked about last time, sometimes we do get solutions that are concentrated. They are sometimes referred to as stock solutions. And what we oftentimes will do with stock solutions that are really concentrated is we will do a dilution, and we'll use a more diluted solution. And really a diluted solution is one where there's little amount of solute as opposed to a concentrated solution where there's a large amount of solute. Remember, the solute is the smaller part of the solution. The solvent is the larger part of the solution. And what happens in the dilution is really the only thing that we add is more solvent. A lot of times that solvent is water, but not always the case. But a lot of times we'll sometimes just add more water to the solution to dilute it down. And the reason really why that works is because molarity, again, is really moles of solute divided by liters of solution. So when we add more solvent, like water, we're actually increasing the bottom number there. So this bottom number is increasing, which means that we're dividing by a larger number, so the molarity comes down as we dilute it. So as we have that more solvent, the liters of solution increases, bringing down the molarity to a lower number and being more dilute. The one thing that doesn't change, the moles of the solute. So the moles of the solute before and after the dilution will equal each other. They're the same. It is really the solute that reacts when a reaction takes place. So if you dump that solution into another solution and they want to react, it is really the solute that's floating around in there that does the reaction. So when we add more water or solvent to it, it has no effect on anything other than it lowers the concentration of that particular solution. Any questions on that? So there is an equation that we use for dilution, and most people will use this equation. Personally, I do as well. That is M1V1 equals M2V2, and that is molarity times volume equals molarity times volume. Usually the ones, and it doesn't always have to be this case, but usually the ones are more concentrated. The more concentrated solution. The twos are usually the more dilute solution. M1 is the higher concentration. V1 is the volume of that higher concentration as you need to use to make your diluted solution. M2 is the molarity of the more dilute solution. And V2 is the final volume of the solution that you want to make that has a lower concentration. Now, in this particular formula, and if you do use this dilution equation, which is sometimes referred to, you can, if you want to leave your volume in milliliters, it will work out okay. So this is the one place that if you're specifically using this equation, you could leave the volume in milliliters, it'll be okay. You could also convert it to liters and it will be okay, whichever way you want to do it. The reason it will be okay, let's just say we were solving for V2 in this case. V2 would be M1 V1 divided by M2. If we just look at units, that would be molarity times milliliters divided by molarity. They will cancel and we'll be left with milliliters, so it would be okay. If you solve for M2, which would be M1 V1 over V2, and we did those guys in milliliters, this would be molarity times milliliters divided by milliliters. Milliliters would cancel and you would end up with molarity. And this is because you're dividing by milliliters, so your millimoles and milliliters will cancel each other out and bring you back to moles per liter. If you want to convert it to liters, you can, or you can leave it in milliliters. But just to be certain, if it is not a dilution, you are not using this equation, and you're using molarity and volume, you need to convert it to liters. Otherwise, you'll get the wrong answer. So if you just want to be safe, just convert it to liters everywhere, and you'll always be safe probably in most cases. But again, this is one place where you could, if you wanted to, leave it in milliliters. Any questions on that? Now, some people and a lot of books will use a more generic version of this equation, which is C1V1 equals C2V2. And it's basically the same equation where C is just generic for concentration and V obviously is volume. And that is because technically speaking, you could use any concentration unit you want. So if you want to do like percent mass to mass on both sides, you could do that. You do percent volume to volume. You can use any type of concentration unit. Most people use M1V1 equals M2V2 because molarity is pretty much the most common unit of concentration. So that's why people usually use that one. But technically speaking, you could do this equation with any concentration unit on both sides. Clearly, in this formula, whichever one you choose, the units of concentration need to be the same on both sides, right? And the volume need to be the same. Again, you can't have 1 milliliter, 1 liter, or something like that. So they do have to be obviously the same on both sides. Otherwise, again, you'll be off by that factor of whichever one you chose. All right, so let's take a look at one here. Let's say we want to know the volume of 19 molar sodium hydroxide that must be used to prepare 1 liter of 0.15 molar sodium hydroxide. So take a couple of minutes here and see what you come up with. So pretty much we have a bottle here of 19 molar sodium hydroxide. And we want to make another solution that has a total volume of 1 liter, which is 1,000 milliliters. And we want it to end with a concentration of 0.15 molar. So we can use obviously our dilution equation here to help us out. We're going to do a little M1V1 equals M2V2. Again, the more concentrated solution would be on the ones. So that's going to be 19 molar times V1, which we don't have. We want to end up with a concentration of 0.15 molar and a total volume of 1 liter here in this particular case. By the way, it's just sodium hydroxide to sodium hydroxide. So really all we're doing is adding water basically to this to dilute it down. We're going to send our 19 molar to this side, and that would give us a V1 that's 0.0079 liters. Or if you wanted a little easier number to look at, 7.9 milliliters of our sodium hydroxide in this particular case. So what does that number basically represent? It is how much of the more concentrated solution you would take out and put into your new bottle here. And we would put in there 7.9 milliliters. Now I want to end up at a 1 liter or 1,000 milliliters. Should I put 1,000 milliliters of water in with it? I should not, because if I did, I end up with 1,007.9 milliliters, right? Which is too much over a liter. So a lot of times when you're in these type of problems, sometimes they will ask you how much water you need to add or solvent you need to add. So a lot of times the volume of water is V2 minus V1. And in this case, we want it to end up, I'll just do it in milliliters, 1,000 milliliters. We already put in there 7.9 milliliters. So if we take 1,000 minus 7.9, it tells us that we need to put in there about 992.1 milliliters of water. So we would put that in there, 992.1 milliliters of water. Give it a mixy, shaky, maybe not so much shaky. And we should end up with 1,000 milliliters or a liter of a solution that should now have a concentration of 0.15 molar. Any questions on that there? In this particular problem, you can leave the answer in liters or milliliters. Most of the time, you probably would leave it in liters since the original volume was in liters, but you could technically do either one in this case. Either question? All right, let's try another one then here. What volume of water is needed to prepare 500 milliliters of a 0.25 molar calcium nitrate solution from a 5 molar calcium nitrate solution? Okay, so kind of a similar situation. We want to make a more dilute solution here, calcium nitrate. We're starting with a more concentrated solution. So once again, we have kind of a 5 molar bottle sitting there, and we want to make a new one that is 500 milliliters and a molarity of 0.25 molar. So once again, we're going to use our M1 V1 equals M2 V2. In this case, we will solve for V1 once again, as we have our more concentrated guy of 5 molar times V1 equals our less concentrated and our volume we want to make in this case. Once again, sending that to the other side, I'm going to leave it here in milliliters, and it's going to be okay. Once again, those units are going to cancel out. So I can, if I want to, leave it in milliliters, if I write the right number. If you want to convert to liters, that is perfectly fine as well. The only difference is you'll end up with liters when you're done rather than milliliters. So our molarity on top and bottom will cancel. Will leave us in milliliters, and we will end up with 25 milliliters. That once again is not the answer to the question, right? Because that number represents how much of the stronger solution we need. So once again, here we would take out of the stronger guy 25 milliliters, which means to find the water, which is really what it asked for, we need to take our volumes and subtract them. So we want to end up at 500 milliliters. We already put in there 25 milliliters, which means 475 milliliters of water would be necessary here. So we would add 475 milliliters of water. Again, give it a mix, and we should end up at that number there. Any question on dilution? Very common dilution problems is more so than the 25 milliliter question. A lot of times they'll ask how you'll make it, how much water do you need to add. So those are very common sort of dilution type problems. Any questions on dilutions? Okay, the next thing we're going to talk about then with solutions is now that we talked about molarity, we've talked about stoichiometry before. We're going to talk about really stoichiometry that involves solutions. The good news is it really is the same steps that we've done in any traditional stoichiometry problem, which is the 4 basic steps, which is you need to balance the equation. You need to convert whatever they give you to moles. You need to do the mole-to-mole relationship and then convert those moles to some other unit. In addition, if it happens to be a limiting reagent type problem, you do need to do a calculation to figure out the limiting reagent. And so you can come across a limiting reagent type problem in a solution stoichiometry, just like a regular one. The main difference in a lot of these calculations is, especially with solutions, is somewhere along the way you're going to use molarity and probably volume and moles. So very commonly up front, you would use molarity to solve for moles. And again, you would take liters times the molarity. Again, needs to be in liters. And very common at the end, you may use the moles that you calculated in the stoichiometry part and use some volume that was given to you to figure out the molarity of a solution. You may do what we normally do, which is take the moles from the stoichiometry part and convert it to grams using molar mass. You may also figure out the volume of a solution by taking the moles from the calculation of stoichiometry and dividing it by the molarity if they gave you the molarity. So at the end, there's kind of a few different versions you could end it with. In most cases at the beginning there, you would probably do liters times molarity to get the moles. But at the end, you could use the molarity equation in a couple of different ways. You also could just do like we've done before, go moles to grams using the molar mass. But you really do follow the same steps. And again, you got to recognize whether or not that is a limiting reagent type problem that requires a calculation. Any questions on that? So let's take a look at one here together. We want to calculate the mass of solid sodium sulfate that must be added to 250 milliliters of barium nitrate to precipitate out all the ions as barium sulfate. We also want to calculate the mass of barium sulfate formed. We're going to start with actually just the first part of this question, which is this way and back. And we'll save the second part there for a moment down the road here. So it is a stoichiometry problem, which means we do need an equation and we have things in words. So remember, we want to make sure we get the right formulas first, then balance the equation. So we're looking for the mass of sodium sulfate that must be added. So that is a reactant. Sodium is +1, sulfate is -2. So that should give us sodium sulfate that looks something like that. It's going to react with barium nitrate. Barium is +2, nitrate is -1, which means we should get some barium nitrate that looks something like this. You also should be able to recognize this as a double displacement reaction, which means our two positive guys are going to switch partners, right? That is what's going to happen here. Remember that when we predict on the other side, we want to write the correct formula first, not balancing. So we want the correct formula. That means, and put it with my nitrate, which is minus, it gives me sodium nitrate, which looks like this with no subscripts, yes. And when I put my barium, that's +2 together with my sulfate, which is -2, that gives me something that looks like this. Again, no subscripts, looks something like this. That is the solid. Now that I have the correct formulas down, I do need to balance it because it is not balanced. So I'm going to say, looking at the polyatomic ion, I'm going to put a 2 there. And I think that will actually balance everybody out. So we got 2 sodiums, 1 sulfate on each side, and 2 nitrates on each side, and 1 barium. So we are balanced. Any questions on the equation? So now that we got our equation for stoichiometry, we want to take whatever they gave us and convert it to moles. Pretty much in this problem, they really only gave us one piece of information, which is our barium nitrate. We have 250 milliliters of it, and it has a molarity of 0.2 molar. From both of that piece of information, I could calculate the moles, right? Which means, is this a limiting reagent problem? This is not a limiting reagent problem because I cannot get moles of the other reactant. Remember, in order to be a limiting reagent problem, you have to have moles of both reactants, which means you have to figure out the limiting reagent. In this case, it's really just a basic stoichiometry problem because we only have one piece of information given to us. Any questions on that? So because it is a basic stoichiometry problem, we're going to follow our steps, which is, again, balance the equation, which we did. We're going to convert to moles. And in this case, we're going to use volume and molarity to get to moles. That means I need to convert this into liters. I'm going to divide it by 1,000, which means I will end up with 0.250 liters when I divide that by 1,000. I'm going to use my molarity as a conversion factor here. Once again, this big M means I have 0.2 moles per liter of barium nitrate. So we're going to use it just like that, 0.2 moles per liter of barium nitrate. The liters will cancel, and now I have converted it into moles, and that would get me 0.25 times 0.2. Gives me 0.2 moles of barium. Any questions up to there? So that's kind of like our second step, right? So we balance the equation. We convert it to moles. So instead of using grams and molar mass to get the moles, we're using volume and molarity to get the moles. Same idea. The next step is, yeah. You can. You're sort of comboing the steps. So that would be the stoichiometry step, which is what we want to do next. We'll kind of get you there. At some point, you still got to use the volume to get rid of the liters part of it, right? So you can get to the moles. So in this case, we do want to look at the stoichiometry, which is the barium nitrate to the sodium sulfate. And from the equation, it is a 1-to-1 relationship between those. So from the equation, we see that for every 1 mole of barium nitrate, we throw in there 1 mole of sodium sulfate. So that would be our next step here. We're going to do the mole-to-mole relationship, which is the stoichiometry part. That takes care of our barium nitrate to our sodium sulfate here. Moles will cancel. I think I could do that math. That's still the same number, 0.5 moles of sodium sulfate in this case. And that is our mole-to-mole relationship. The last thing is to convert our moles into the units we're looking for. And in this case, we're looking for grams. So now that I've converted over to sodium sulfate, we need to do the molar mass of sodium sulfate. So that's going to be 2 times our 2299 for sodium, plus our 3207 for our sulfur, plus 4 times 16 for our oxygen. And all those numbers obviously come from the periodic table. And that's going to be 2 times 2299 plus 3207 plus 4 times 16, about 142.1. And we'll use that as our final step after we did our third step here, which is we want the grams up on top. So 142.1 grams per mole of sodium sulfate. The moles will cancel, and that will get us, looks like 7.11 grams of sodium sulfate. That technically would be not a yield because that's a reactant. So that's how much of the reactant we would need to put in there. And that obviously would be our fourth step. So by understanding that this is a basic stoichiometry problem, as you can hopefully see, it is still the same 4 steps that we did. The only additional thing is, again, using that volume and molarity to calculate the moles. Question on that there. All right, so with all this information here, why don't you do actually the second part of the question, which is, now that we know how much we need to throw in of the other, how much of the barium sulfate would actually be formed. So why don't you do this part of the question using obviously the same equation. So why don't you do this part here. So take a moment and see what you come up with. I'll give you some numbers that might be helpful. How many grams of barium sulfate would we make? Barium 137.3 grams per mole. Sulfur 3207. And oxygen 16. All right. Based on the same starting amounts, how many grams of that barium sulfate should we produce? Okay, let's take a look. So really in this part, which is the second part of this problem, we kind of have half of it done. We obviously already have the equation balanced. We actually converted to moles, so we could start up with our conversion to moles here. Truth be told, you could also, since we did this as part of the calculation, the other guy, and we have really the starting amounts of those moles, you can use those moles as well. They both will come out the same. But we'll just use our original barium nitrate moles. So we do have our barium nitrate moles, which was 0.05 moles of barium nitrate. And since we're going to use this moles, we want the relationship now between barium nitrate and barium sulfate, which is a 1-to-1 relationship. Again, won't always be 1-to-1, happens to be in this case, so that makes the math not too bad. So that's going to give us 1 mole of barium nitrate from the equation. Gives us 1 mole of our barium sulfate. And that means that we will end up with 0.05 moles of barium sulfate. That would be the theoretical yield, as that's a product in moles. But we are looking for grams, so we do need the molar mass here of barium sulfate. So that's 137.3 grams per mole for the barium, plus 3207 for the sulfur, plus 4 times 16 for the oxygen. That's going to give us 137.3 plus 3207 plus 4 times 16. Looks like 233.3 grams per mole as our molar mass. And that will be the last thing that we need here to convert these moles into grams. So that's going to be a 233.3 grams per mole of barium sulfate times 0.05 gets us about 11.7 grams of barium sulfate would be produced in this case, and would be our theoretical yield of barium sulfate. Once again, because the first part of this problem, we actually had this number, which you could have used as well, and just picked it up with the multiple relationship. Question on any part of that there? All right, why don't you try another one here to finish up with? Let's say on this next one. Calculate the mass of the white solid calcium carbonate solid that forms when 25 milliliters of 0.1 molar calcium nitrate is mixed with 20 milliliters of 0.15 molar sodium carbonate. And give you some numbers. Calcium 4008, carbon 1201, and oxygen still 16. All right, so take a few minutes here, see what you come up with. We want to know how much of that solid calcium carbonate would be formed when we mix these two solutions together. I'll talk about it since we're getting to the end here, just so again we can kind of see what's going on. So obviously it's a stoichiometry problem. So much like all of them, we do need an equation to begin with. So in this case, we're going to take some calcium nitrate solution and we're going to mix it with some sodium carbonate. And once again, you should be able to recognize this as a double displacement reaction. Two positive guys will switch partners as they are two ionic compounds coming together. Again, as we did in the last one, we want to get the correct formulas first. So calcium is +2, carbonate is -2, which means we should end up with something like this, which would be our solid. And our sodium is +1 and our nitrate is -1, which means we should end up with something like this. Now that we have the correct formulas down, we want to make sure we balance it. And again, it looks like perhaps all we need is a 2 right up there. Any questions on that? At this point, we want to look at what was given to us. So we have calcium nitrate. We have 25 milliliters of it, and it has a molarity of 0.1 molar. We also, for our sodium carbonate, we have 20 milliliters of this one and a molarity of 0.15 molar. From both of these pieces of information, I should be able to get the moles for both. That it is a limiting reagent problem. And that means that you do need to do a calculation, by the way. To calculate the limiting reagent, you can't just pick whichever one you like. You actually have to calculate which one is the limiting reagent. So this is going to be a stoichiometry problem, but we are going to have to do the limiting reagent step in there. The second part is really still the same. We're going to convert everybody into moles. So if we take our calcium carbonate, divide our 25 milliliters by 1,000, that will convert it into liters. We'll times it by our molarity of our calcium nitrate here. And that will give us for our calcium nitrate 0.0025 moles of calcium nitrate. We'll do the same thing for our other reactant, which is our sodium carbonate, dividing the 20 milliliters by 1,000. We'll convert it into liters using the molarity of 0.15 moles per liter of our sodium carbonate. And that will get us 0.003 moles of sodium carbonate here. Any questions on that? Again, liters obviously would cancel. Because it is a limited reagent problem, remember we want to do a simple calculation to determine if I want to use up one of my reactants, how much of the other one is needed. So if I want to use up my calcium nitrate, I will do that calculation, which is 0.0025 moles of calcium nitrate, which is what I want to use up, using the mole to mole relationship between the calcium nitrate and the sodium carbonate, which happens to be a 1-to-1 relationship, which is nice. That will tell me how many moles of my sodium carbonate is needed. And that would tell me I need 0.0025 moles of sodium carbonate is needed. And I would compare that to my starting 0.03, and we do have enough. Which means that this guy here would be my excess reagent, and this guy would be my limiting reagent. So once again, you do need to do some type of calculation to determine that. Yeah. Any questions on that? Now that we've actually determined that, I'm going to borrow some of the room up here to finish it out. We are going to start with our limiting reagent and figure out how much of our product we would make. So using our limiting reagent starting amount, which is here, we would go with 0.0025 moles of calcium nitrate. We're now going to do the mole to mole relationship between calcium nitrate and our product here, which also happens to be a 1-to-1 relationship. A reminder, they won't always be a 1-to-1, but happens to be in this case. 1 mole of calcium carbonate from the equation that's balanced gives us 1 mole of calcium nitrate. The moles of calcium nitrate cancel, gives us 0.0025 moles of calcium carbonate. That would be our theoretical yield in moles, but we want it in grams, so we'll use our molar mass here to figure out the molar mass of calcium carbonate, and that is 4008 for the 1 calcium, 1201 for the 1 carbon, plus 4 times 16 for our oxygen, which is not 16. It is 5209 plus 3 times 16. It's 100.1, it looks like, grams per mole. So using that to figure out our grams that we would produce, the molar mass from the periodic table tells us we will end up producing, in this case, about 0.25 grams of calcium carbonate. That would be our theoretical yield in grams. If this problem was different and we had, say, the molarity of calcium carbonate, we could have figured out the volume. If we knew the volume of calcium carbonate, we could have figured out the molarity. So again, there's a few options at the end there. Any questions on any of those steps there? All right, we'll lay it up there.